what I was interested in is to see if we could get a better model if we incorporated climate data in as well as the optical data from Sentinel. What I had to do is look into how that climate data might impact what the satellite picks up. And so there are two different ways it can impact it. One is the climate data could directly impact the algae biomass, either because the precipitation, especially in the spring, might increase the amount of nutrients that get loaded into the Western Basin from fertilizer or that kind of thing. And then second of all, because of the temperature range and how that impacts how quickly the algae grows. And I said cyanobacteria specifically here just because that's the type of algae that we're most interested in since it's associated with the toxins. The other thing that could impact the model is that different climate data could impact the actual optical properties of the algae bloom kind of separately from just its biomass. And so that could be the community composition of the algae bloom. So different types of algae have are like different colors or different shapes. And also, if the water gets mixed a lot, then you're going to see less, like the satellite is mostly picking up what's on the surface of the water, right? So if there's a lot of mixing, then there may be much more of a bloom than what we see just because it's no longer on the surface. The mixing can also impact how quickly it grows. And then the other thing that can impact the optical properties is the turbidity level of the water. That's just a little bit of background on kind of the premise of looking into the climate variables and how they might impact algae. What I found when I was reading up about this is there are many ratios that people commonly use to model chlorophyll. We can't directly measure right now the amount of like cyanobacteria or microcystis in the water, so we just look at the chlorophyll level because it's associated with the size of the algae bloom. And so the goal ultimately would be to create a chlorophyll-a map of Lake Erie. The previous student had already figured out these two ratios as being pretty good for modeling chlorophyll. And then just from the reading, these are a couple also commonly used ratios. Then DCI is commonly referred to as the chlorophyll index. The fluorescent violet ratio was originally designed for Landsat. Bands are a little bit different between Sentinel-2 and Landsat, but it works pretty well still. And then I have it was referred to in this paper as 2-band DA. I can't remember what DA stands for, but this was also came up a lot. So I'm just gonna read in some data. We'll just view the top of that. The date, the EPA station, a bunch of data from the EPA, and then eventually we have some of the climate data that I pulled in from the University of Idaho Climatology Lab. So we have the temperature that day, air temperature, and precipitation, and then I'm not doing any kind of like time series modeling. So in order to incorporate, the past data, then I just took like a simple moving average. We have our Sentinel data and then ratios. So ratio 1 and 2 were those that the previous student had already figured out. And then we have the chlorophyll index, fluorescent violet, and this S2BDA. The next thing I wanted to talk about was whether or not linear regression would be appropriate or inappropriate for this data. And with linear regression, whether it's univariate or multivariate, there are certain assumptions that have to be true in order for the conclusions of the regression to hold. This is just kind of a summary of what those are. We assume that there is actually a linear relationship between the response and the regressors, and then we assume a bunch of things about the error terms. This is just the ratios against the extracted CHLA and the natural log extracted CHLA. We can see that there's something there, but it's not particularly strong. The best linear relationship between extracted CHLA is with the Sentinel 2-band DA at 0.51 as a correlation value, which is okay, but not amazing. And the rest are lower than that. Natural log does a lot better. Most of those are around 0.5, but we'd like to see whether there really is a linear relationship there, or if there's some other pattern going on that would result in better predictions. So the goal is really to have more accurate modeling. And we don't want to run linear regression if the assumptions are met, because then the results are probably not as good as they seem, and that can be really misleading. Another way that we can look into the relationship between variables in R is just a scatter plot matrix. This one's a little small, but I can zoom in. This is basically the same thing as a correlation matrix, except we can actually see the pattern here. With the extracted CHLA here, can see that there's not really what we would normally call like a really close linear relationship, but that might be partially because of the scale. We can see that we have a couple like outliers here that have really extremely high values of extracted CHLA. So there might be something here that's being really heavily impacted by the outliers. We see much closer to a linear relationship with the natural log extracted CHLA, but maybe it's a little curved here, like the chlorophyll index and the natural extracted CHLA definitely looks a little curved. It's definitely worth looking into whether or not linear modeling would be appropriate. This for loop will go through each of the ratios that we're interested, 1, 2, the NDCI, fluorescent violet, and the Sentinel 2-band DA. And it will individually fit each of them to the extracted CHLA. It will print out a plot of the residual plot and the QQ plot, and then it will also print out the results from the Shapiro-Wilk test, which tells us whether or not the errors are normally distributed. Lots of plots. Okay. And with the Shapiro-Wilk test, you know, we just want to know, are the errors normally distributed? The null hypothesis is that they are normal, and the alternative hypothesis is that they are not normal. And so if our p-value is small, then we reject the null and we say they're probably not normal. So here we have a very small p-value, less than 0.05, and so we would say that for ratio 1, if we just fit a basic simple linear regression with ratio 1 and extracted CHLA, the errors are definitely not normal. Same thing for ratio 2, very small, not normal. Chlorophyll index, very small p-value, not normal. And then we have fluorescent violet, very small p-value, not normal, and the same with the 2-band DA, not normal. So that's just also confirmed here. We've got a residual plot. This is ratio 1 is first. If it was perfect, then we would see that they're the residuals look random. The mean is close to 1. We see a little bit of a pattern here. It's actually not too bad. If it wasn't for the outliers, maybe. We can look at the QQ plot as well. And this pattern here, so the dotted line, in case you're not familiar, the dotted line is what we would expect from a true linear relationship. And so the fact that it's deviating here at the tails tells us that the true distribution of the residuals is probably, I think I said weak-tailed, so much smaller tails than what we would expect. So we've got much more congregation in the middle. So we could look at all of these kind of similar patterns here with the QQ plots. We've got some kind of skewedness going on. It's not terrible, but it's definitely not normal. We can do the same thing with the climate variables. So this is, again, just looking at the extracted CHLA against the climate variables, natural log CHLA against the climate variables, and again, we see there's not a really strong linear relationship there. This is the same thing with the climate variables. I just split up the first one as precipitation, and our precipitation values are really, really skewed. We have very little, most of our values are little, we get a couple really big values, even for the 3-day, 7-day. You can kind of see that definitely not linear. Before I was just fitting simple linear regression, we can do the same thing but fit our climate variables and each ratio individually for multivariate linear regression. What I did here, since all the climate variables are really correlated with each other, we can't do like today's precipitation, 3-day precipitation, 7-day precipitation. So I just chose 7-day averages for each of the climate variables to test the normality assumption. And again, we see that our p-values are really small for all of these. And so normality is probably not the best assumption. These look almost the same as before. This is funny, you don't want to see this with a residual plot. So the point is that it'd probably be worthwhile to look into alternative modeling options if we have them. I guess I decided to be really extensive with this. So this is with the natural log, same idea. Probably a linear relationship is not the most accurate way to model this. Why don't we try some other things? Here, I'm just selecting testing and training data so that we can do cross-validation. In order to make it easier, since I'm running the models repeatedly, I just created a function to do that where I can specify which variable I want it to run on. Basically, what I was afraid of is that I would make some error by just creating this function to run it for me. I felt like that was a safer option. I did the same thing with the boosted tree, and then I just created this function to calculate the test MSE for any of our models. So then here, I'm just fitting a bag tree on the extracted CHLA. We create a list to store the models in, and then we create a vector to put the test MSE for each model in, and we want to fit it for the climate variables, the 7-day precipitation, 7-day min temperature, 7-day max temperature, and one of the ratios. And so the ratio changes each time we fit it. We have 5 ratios, so we fit 5 models. We use the training data, and then since we're doing the bag tree, our variable number is equal to the number of variables we have to fit. So we do that. And then here I just calculate the test MSE for all of those. And then the display MSE function that I showed you up above just tells us which one was the smallest. It was the smallest for the chlorophyll index, and it was 913, which is pretty big. So this model is not very good. When we do the same thing for the natural log CHLA, we get a much better model with the test MSE of 0.74, and for ratio 2. So I'm going to keep doing this for all of the models, and then at the end we'll just compare test MSE for all of them. So this is random forest for the extracted CHLA, still very high test MSE. We can do natural log, much better. This is a boosted tree, very bad. So we can see natural log is definitely working out a lot better for us. And then at the that's pretty much everything. We already saw all of this. I'm just reprinting it so that's easy to see. The best one in this case was the natural log random forest, but it's very close to the other ones that we fit with the natural logs. They all got very close test MSEs with this data this is all data from 2019. Finally, I'm just reading in Sentinel-2 data from 2016. to see how this model does on data from 2016. So this is the Sentinel-2 data again, and then I just added those temperature or those climate variables. Since the best one uses a chlorophyll index, is just to calculate the chlorophyll index on the new Sentinel data, and then we can get the test MSE on the data from 2016, and we get 2.38. We can see that it's definitely a little bit higher. We can look at the residuals. We definitely see a pattern here. So the conclusion of this is probably not the best model, but that's kind of the process, the starting process for going through and evaluating models and seeing what the test MSE is for all of them. And hopefully we can find something better.